Now we will see another example of shortest job next, but this one is a little bit complicated. Why? In the last one, okay, in the last one, as you have seen, all of the jobs arrived at the same amount of time. That means 0, 0, 0 second. Okay, but in this one, okay, in normal cases, all the jobs doesn't arrive at the same time. They arrive at a different amount of time. So this job may arrive at first second, this one at the second, this one the third second, and so on. Okay, now all the jobs here arrive at a different amount of time. So in that case, okay, how will our Gantt chart will look like? So let's start. So at the 0 second, as you can see that there is no process. So that means from 0 to first second, the processor will sit idle because there is no task. So if in the exam, if you face cases like this, you will just skip this part. This might be 0 to 1 second, this might be 0 to 5 second. It doesn't matter the amount of time. If there is no process in a certain amount of time, in that case the time is idle time. Okay, and then after the first second, as you can see, we have the process number 1. Okay, so now in the shortest job next, what we do in this one, if you see, we have assigned a CPU to the shortest job. Here the job was job number 4, so we assign the CPU to the job number 4. Now if I go for this example, initially which one is the shortest? P3, right? With only 1 second. But if you look at the Gantt chart, process 1 was assigned the CPU first. Now why did this happen? Because at the first second, okay, at the first second, when the CPU was checking for the shortest job, there was only one job, and that was process 1. So process 1 got the CPU, and then it kept running until 8th second. And when it was 8th second, okay, then all the process arrived. Okay, and in that time there was a process 2 was present, process 3 was present, 4, 5, everyone was present, because their arrival time is less than 8th second. And then after, out of this 4, which one is the shortest? P3 is the shortest. So P3 was assigned the CPU, and then P4 was the shortest, so P4 was assigned. So everything is normal now. But this is the part that we have to actually be careful in the exam, because sometimes we make mistakes in this part. So let's let's give you 5 minutes and solve it. Okay, so everyone had the correct answer. Now one thing that you actually have to notice here, that in this one, when we will calculate the average waiting time and the average turnaround time, you see that this shortest job next technique that we were saying, that this is actually the best possible in the non-preemptive process. Again, non-preemptive means that once the CPU is allocated, it will not taken back. So in the non-preemptive system or the scheduling, this shortest job next is the best one. But we see that in case of shortest job next, we can also suffer from convoy effect. And what is the convoy effect? That you see here, the process 1 arrived at first, and because no other process was there, he got the CPU, he spent a long amount of time, and all other processes were only 1 second, 2 second, okay, they had to wait a long amount of time. So even this shortest job next is actually not free from convoy effect. So what we can do actually to solve this issue? To solve this issue, what we do, we use the shortest remaining time scheduling, and this is basically the shortest remaining shortest job next algorithm with preemptive. That means we allocate the CPU, and after certain amount of time, we check whether there is any short process or not. If there's any short process, we take back the CPU and allocate it to this one. So if I go back to our last example to put it in the context, like in this one, the process 1 got the CPU first. Okay, so what will happen, that we will allocate the process 1 first, as there's no other. But after a certain amount of time, that time may be 2 seconds, that time might be 1 second. Okay, what we will do, we'll take back the CPU. Okay, and we'll say that, okay, let's check again whether there is any other process or not. Okay, and in this way we will keep going on. So we will first allocate the CPU, and then we'll check after a certain amount of time. And if there is any, if there is other process which are actually shorter than this, in that case, we will take back the CPU from process 1 and we'll allocate it to process 3 or process 4 or so on. And that's how the shortest remaining time work. Okay, the processor is allocated the job closest to the completion, but it can be preempted by a newer ready job. So that means it was allocated to a process 1 who had 7 seconds. Okay, but suddenly there was a process 3 who had a newer ready job which was process 3 with a shorter time to completion. As we have seen, the P3 only needed 1 second. Impossible to implement in an interactive system where required CPU time is not known. Again, the same problem. We have to know that each process how long it will take. To put it in the perspective, whenever you actually try to download something, we can exactly see that how much time is remaining. Okay, but whenever you connect, you're using Facebook, the operating system actually doesn't know how much time you will use it. Okay, how much time you'll be using Facebook. So some of the processes are not actually known, and it is often used in batch environments where short jobs needs to be give preference. Okay, so when we have a multiple jobs we are conducting at the same time, and we give preference to the short job. Also, there's a priority matter, I will discuss it later, but let's first now focus on this math. Okay, so we will see that given these conditions, we have how we can actually use it for shortest remaining time.